You guys had a good exam, so um, we'll have one more final exam. So whatever material I'll start from today will be on the final, so final will not be comprehensive. So anyway, so to finish the topic of pipelining, we had discussed that as we pipeline a processor, to improve the performance, we run into three kinds of problems, which are called hazards, right? So we can run into what are called structural hazards, or data hazards, or another category that I'll introduce today is control hazards. So these are basically problems in pipelining. That's what we call hazards, right? So as we discussed, structural hazards occur due to resource conflicts. So within the same clock cycle, if we are trying to access a resource could be memory, could be ALU. So this could be memory, could be ALU, okay? Or any other hardware that we have inside the CPU. If in the same clock cycle we are trying to access and we have a single resource, obviously we have a conflict, right? So the key thing to remember is that we want to avoid the hazards, okay? So we should try to avoid the hazards. And why? Because they destroy the performance. Okay, so for example, let's say on average, let's say due to hazards. So due to hazards. Okay, suppose we need three stalls per instruction. So remember the stall was, let's say this is our pipeline. This is our program counter. We read from the data memory, instruction memory. Then we go to the instruction register. So this is one clock cycle, right? So very similarly, in the second clock cycle, we decode, copy into A and B, correct? In the third clock cycle, we go through the ALU, produce some result in ALU out, right? Then we go through the data memory, produce some result in LMD, and then finally try to write it back to the register. So we had this 5-cycle pipeline, right? Okay, stall was basically if there's a dependency or there's a problem, then basically the instruction does not move forward, it just stays right there, right? So if we are not moving forward, staying in the same place for 3 clock cycles, right? Let's pretend on average this is what happens. Then what does it do to the performance? Our performance, if you recall, was measured by the weighted cycles per instruction. So CPI, so that means 70, let's say 70% of the time we are able to accomplish, or let me say this, on average, due to hazards, okay, suppose we need 30% of the time. We need 3 stalls per instruction, right? So then our CPI will become 70% of the time we are finishing each instruction in 1 clock cycle, and 30% of the time we are finishing it in 1 plus 3 clock cycles. So what happens to our total CPI? 0.7 plus 1.2 becomes 1.9. So if 30% of the time we are wasting 3 cycles, you can see the performance reduces by 90%. Okay? Our ideal CPI, meaning ideally we want to finish 1 instruction in 1 clock cycle. Okay, so that's why it's very important to try to avoid hazards. And how do we avoid that? By providing more hardware, as you guys have seen. So anyway, let's come back to the categories of hazards. Structural hazards occur due to resource conflicts. So for example, let's take a look. We have add, let's say R5, R3, R7, subtract R6, R4, R8, let's say load word, R5, R7 of 20, right? So we have a set of instructions, and let's say we have multiply R8, R9, R13, something like this, right? So let's take a look at, will we have a problem over here in executing these instructions? And if we run into any hazard, how will we solve that? Or as you will see, we'll provide more hardware so that we don't have to stall. So we have to try to avoid the stall. That's the key idea. Okay. So every instruction goes through 5 stages, as you guys already know now. Instruction fetch, instruction decode, execute, mem, and write back. Correct? If we are pipelining, this will start 1 cycle later. So IF, ID, EX, mem, and write back. This will start 1 cycle later. IF, ID, EX, mem, and write back, right? And again, the last one will start 1 cycle later. IF, ID, EX, mem, and write back. Okay, let me change the second instruction, or let me make the let me make this the load word instruction, and let me change this to a multiply instruction, so that I can explain one idea over here. So suppose this was R12, R14, R16, and let's make this load word R9, R3, R20, something like this, right? Okay, so if you take a look at, let's say this is clock cycle 1, 2, 3, 4, 5, 6, 7, and so on. Okay, let's focus on clock cycle 5. Okay, in the clock cycle 5, what you will see is, okay, actually, let's go to clock cycle 4. Okay, let me change one more thing over here, one more time. Let me make this a load word. Load word R7, R3 of 20, and let me make this add something. Add R8, R6, R4. Okay, this will be better. Okay, so if you take a look at a load word, and let's focus on clock cycles 4, not 5. Okay, so let's focus on clock cycle 4. So you will see load word is trying to access the memory, right? Okay, and also the add instruction over here, add is basically doing a fetch. So the fetch is also coming from the memory. So this is fetch from memory. So this is an example of, as we had discussed before, an example of a structural hazard. Okay, we are trying to access the memory in 2 different instructions. The memory is being accessed by 2 different instructions, but in the same clock cycle. Clock cycle 4, load word is accessing the memory. Clock cycle 4, add is also accessing the memory. So if we only have one access point to the memory, meaning one way to read or write to the memory, obviously both of them cannot read and write at the same time. So we have what we call a hazard, and either we have to delay the instruction. So one possibility would be to delay this instruction, put a stall over here. IF, ID, EX, mem, and write back. Okay, so meaning don't try to fetch it, because let this finish the memory, then we'll try to fetch it in the next clock cycle, right? But now if we move it over here, take a look over here, again there's a possibility. This is the second instruction may be accessing memory, and we are fetching from the memory, so again there might be a problem, right? Okay, so easy solution as we came up was, let's split the memory. Let's split the memory into instruction memory and data memory. This way we won't have to delay this and put a stall over here. So this will be simply IF, ID, EX, mem, and write back. So this one basically will access the, which memory? Instruction memory or data memory? See, this is trying to read from the memory, right? So by the time we come over here, this is really the data memory. And where are we trying to fetch the instruction from? Instruction memory. So if they are physically two separate memories with their own address lines, data lines, read-write signals, then simultaneously reading, writing to this does not affect reading, writing to this, and both of them can go at the same time. So in our hardware, we solved one of the structural problems by splitting the memory into data and instruction memory. Okay, so one type of structural hazard that we ran into was the memory. Okay, and how did we solve it? We said let's split it into instruction memory and data memory. So this way we won't have to worry about resource conflicts on the memory. Two instructions can simultaneously access them as long as one of them is accessing the data memory, the other is accessing the instruction memory, right? Is there another possibility for a structural hazard in our current design? So let me show you another problem. Okay, so far we assume that when we go to the ALU, which is our EX phase, it will be able to add or subtract or multiply or divide in one clock cycle, right? What if ALU is slow? It takes 2 clock cycles to finish each instruction, right? Like add or subtract. So if ALU is slow and takes, let's say, 2 cycles to finish its execution, okay, so whatever we asked it to do, like add or subtract or multiply or divide, if it takes 2 clock cycles to finish, then how is this going to change? Then this is going to become, let me pick a different example. Okay, so then suppose we have add, R7, R3, R5, subtract, R6, R4, R8, multiply, R12, R14, R16, and so on, right? Okay, so let's try to see how this will affect IF, ID. Okay, to indicate that ALU is going to take 2 clock cycles, what we will do is we'll put EX1 and EX2. So rather than just one EX, we'll put 2 EX1 and EX2, and mem and write back. Okay. Same thing over here, IF, ID. Okay. So now take a look over here. As the second instruction, see this is where it's trying to use the ALU. EX is where the ALU is involved. So here's our ALU. Okay, and before the ALU, if you remember, we had copied the data into A register, the B register, right? And through the muxes, we were basically feeding it to the ALU, and this was going to the ALU up. Okay, so now we are saying the delay over here is equal to 2 clock cycles, okay? So obviously, if add instruction is somewhere over here, is trying to have the ALU do the addition, can the subtract instruction also go and start modifying the circuitry before the add is done? See, so this is where the problem is. If we go for the subtract and we try to do EX1, the add is already in the second part of it's not fully done yet. So we'll end up disturbing the result of the add instruction if we also change the data on the input of the ALU and make it according to the subtract. So this is what I'm saying cannot be done because ALU is still not done yet. Okay. So how do we solve this problem? By one option is we have to put a delay over here. Okay. So this is what we call the stall or the bubble. So we'll basically put a stall over here, right? And then we will start EX1, EX2, and MEM and write back. Okay. So how is this going to affect our performance? Okay, the CPI. So again, let me assume, so suppose 40% of the time, okay, ALU, we find the ALU is busy. So we have to put a stall or a bubble, okay, meaning delayed. Okay, so what will happen to the CPI then? CPI, 60% of the time it will be done proper, it will do proper pipelining, will be done in 1 clock cycle, right? And then 40% of the time it will do 1 + 1 because we are putting an extra delay over here. So what happens to the CPI then? So 40% loss in performance, right? So how can we, so first of all, what kind of problem is it? Is it a data problem, a control problem, or a structural type of problem? It's the ALU, which is a resource, right? Remember, structural hazards occur due to, so 2 instructions are trying to use the ALU, but we only have 1 ALU, so obviously one has to wait. So that's one more example of a structural hazard. One option is just leave the stall and let it continue, but then nobody will buy our CPU because it will be too slow, right? So this will be like AMD versus the Intel type of CPUs that continuously they are fighting over which CPU is faster, right? Okay, so alternatively, if we do not want a stall, then as I mentioned, by providing more resources, we can overcome this. So general strategy for overcoming structural hazards is provide more resources. In case of memory, we just split it up. Unfortunately, ALU we cannot split, but we can provide more than 1 ALU, right? So from a pipelining point of view, think of it this way. Okay, rather than drawing the full data path over here, suppose this is our IF phase, which is really the program counter reading from the instruction memory going to the instruction register, right? Then we have the decode phase, which basically reads the register from the register array, copies it into A and B, right? So let's put EX over here and MEM and write back. Okay, so now because we are assuming ALU is slow, it takes 2 clock cycles, so I'll replace this by EX1, EX2, MEM, and write back. Okay, so from a pipelining point of view, we have 2 options. See, our goal is not to put a slowdown over here. So one option is, so option 1, okay, pipeline the ALU internally. So if, remember some time ago I had talked about the concept of pipelining. If you have a combinational logic, okay, and you have some register over here which feeds the data to the combinational logic, whatever it produces the result, we clock it into the into another register. So let me call this R1, let me call this R2, right? Okay, so for example, if the delay over here is 5 nanoseconds through this combinational logic, that means the clock that we have over here has to be greater than 5 nanosecond time period. Okay, so this t has to be greater than 5 nanosecond, otherwise we will not be able to produce the correct result before we store it in our destination register. And remember, frequency is 1 over the time period. Okay, so our frequency has to be bigger than 1 over 5 nanosecond. Okay, if we wanted to speed it up, one option would be if somehow we are able to split this combinational logic in 2 parts. Okay, so suppose we are able to split it in 2 parts. So we do half the logic, then we transfer it into another register. And then, so then the idea will be, as first data comes in, passes through half the combinational logic, goes over here. As this goes over here, new data can come in over here. We don't have to wait for the entire delay. So we can cut it down to 2.5 nanosecond, right? So same thing over here. If we are able to internally pipeline the ALU, so if somehow we are able to do that, then what we'll do is we'll put something like this. So this will go into EX2. Okay, so then this is not a problem because if there's a register in between over here, so there's a register over here, then from pipelining point of view, let's say the add over here goes to EX2, so the add is over here, right? Because the intermediate result has already been stored in a register. The next instruction, in which in our example is a subtract, so the subtract can go over here. Okay. So what I'm trying to say is, if the ALU is internally pipelined, then it's okay to proceed. So then it's perfectly okay. We will do ID, EX1, EX2, mem, and write back. Okay, same thing for the next instruction, IF, ID, EX1. As long as there's no data dependency, they can proceed simultaneously. Okay, so if ALU is internally pipelined, and there's no data dependency, okay, we can proceed normally without a stall. Okay, so again, this was under the assumption that somehow we can split the ALU into 2 halves and store the intermediate result in a register. This way another instruction can come in without disturbing the half result that was produced. Okay? But sometimes that may not be possible because ALU is pretty complicated. It may have some, let's say we are doing some sine, cosine, or square root computation, and it cannot be really split in half that easily, right? So that was option 1, pipeline the ALU internally. If that does not work, then option 2 will be provide more than one ALU. Okay, so let's take a look at the second option now. Okay, so in the second option, this is what we'll do. Okay, we have our fetch phase, which will go to the decode phase. Then this will be our EX1, EX2, then mem, then write back. Okay, and over here, so this is our ALU1, and this is our ALU2. So we have two ALUs. Okay, and they are not internally pipelined. Okay. So now, so that we can distinguish which ALU is being used, let me call this EX1A and EX2A. So pretend this is, let me call it ALU-A over here. So this is our ALU-A, and this is second ALU, let's call it ALU-B. So this is EX1B and EX2B, right? Okay, so now let's go over here. Obviously, if the add instruction is going through the pipeline, right, it will follow the top path over here. So this will follow the A and A. Everybody agrees? Okay, let's go to the second instruction now. Once the second instruction tries to use the ALU, remember it's not internally pipelined. That means if one instruction is not done with the ALU, second instruction cannot use it, right? So which one should we use over here? The A or the B? B, right? Because A is not done yet. So we know this should be B and this should be B. Okay, but the question now is, how does the hardware know that from here we should go over here and not go over here, right? Easy way to do that is we can put a flip-flop over here. So we can put a busy. So A is busy, and put one more flip-flop over here, B is busy. So basically our controller checks these two flip-flops. If A is busy, it will check the second one. If it's not busy, it will use this one and set this to 1, right? So for example, let's continue over here. Let's go to the multiply instruction. So once the multiply instruction comes in, how will the hardware decide which ALU to use in this one? Okay, remember it's going to check whether the A is busy flag is 1 or 0. As soon as the first instruction is done using the ALU, top ALU, it will obviously put a 0 over here, meaning it's available, right? However, the sub instruction is still using the ALU at this time, so this is 1, meaning it's busy. Okay, so now once the multiply instruction comes in, our controller will check both of these. Which one does it find to be free? Obviously the top one, so it will now, multiply will use the top one, so it will go to over here, and it will change this flag to a 1, so that it's busy now, right? So this way, we can easily switch between one ALU and the other. And this way, there's no need to put a stall in our pipeline, and the performance will be higher, right? Okay, let me ask you a general question. On the final exam, I'll have something similar to you for you guys. Okay, suppose the ALU is taking 3 clock cycles to finish any of its arithmetic operation, okay? Equivalent of 3 cycles. If you do not want any stall in the pipeline, how many ALUs will we need?
3.
3 ALUs. Okay? If you use 2 ALUs, you'll end up using. What if ALU is consuming 4 clock cycles? Then 4 ALUs. Okay? So we can put more ALUs to avoid the structural hazard due to ALU being needed in more than one instruction at the same time, right? Okay, so that was the idea behind structural hazard, provide more than one resource. If we can internally pipeline it, then one ALU will work. But if we cannot internally pipeline it, we have to provide multiple ALUs, right? Okay, so now let's go to the data hazards. Data hazards we talked about nicely before the exam. So let me quickly refresh your memory and then we'll come to control hazards. Okay, data hazards, as we discussed, occur due to data dependencies. And there are 4 kinds of dependencies that theoretically can occur. We discussed those are RAR, RAW, WAW, and WAR. Okay, so read after read, read after write, write after write, and write after read. Okay, so an example of this was, let's say we do add R5, R3, R7, subtract R6, R4, R3, right? So as you can see, we are reading from R3 over here. We are reading from R3 over here, but reading never changes the register, so no matter what architecture you are creating, RAR is never a problem, okay? So this is never a problem. So this is just for theoretical interest, right? Let's go to RAW. So this can be a problem. Okay. So for example, in this case, so this is read after write, okay? So suppose in this example we are writing to R5, right? And let me change this R3 to R5. So now we are writing to R5, and after writing to R5, we are reading from it, okay? So obviously, if we take a look at the pipeline, this is IF, ID, EX, mem, and write back, right? And then this will go IF, ID, EX, mem, and write back, okay? Okay, so remember the purpose of this was add R3 plus R7. And then store the result over here. Okay, so when do we store the result in R5? If this is clock cycle 1, clock cycle 2, 3, 4, 5. So when do we normally update R5? In the write back, correct? At the end of clock cycle 5, we will write to the destination register. Okay, so suppose R3 had some number 5 in it. In the beginning. R7, let's pretend, had 10 in it, right? So you can see 15 will be written to R5, okay? But let's pretend in R5, in the beginning, we had 6 in it. Okay, so if we waited till the 5th clock cycle, because this is where we read R5 normally. See all the registers in the ID phase, we go to the register array, read the data. So this will end up reading 6, right? And suppose R4 has 12 in it, so 12 minus 6, it will end up producing an answer of 6, which is wrong, okay? It should have been 12 minus, what did I say over here? 15. 12 minus 15, the right answer So right answer should have been -3. Okay, so as we discussed before the exam, through a technique called forwarding, we can solve this problem. Okay, in forwarding, what we do is we don't use the result from the register array. So instead, what we'll do is we will forward the result from here to the input of the ALU. So forwarding was the feedback in our real data path. So this way, 15 will be fed over here to the input of the ALU, so it will use 15 and it will not use 6, and it will end up producing the correct result, right? So, so some of the RAW type of hazards can be solved by forwarding. And as we discussed before the exam, forwarding is actually feedback in the data path. So just to very quickly refresh your memory, if this is the ALU, if this is ALU out, okay, here we had a MUX going into the ALU, MUX going into the ALU, right? Okay, so the add instruction, once it produces R3 plus R7, is over here, R3 plus R7, right? So once the subtract instruction goes through, we don't use the old R5, instead we will use this one. This one will be fed back, and this R3 plus R7 will be used over here, and not the R5. And of course from here R4 will come in. So this is how the subtract instruction will produce by using this feedback over here. The previous result will be fed back to the input of the ALU. So the previous result, which is over here, is fed to the input of the ALU. In this way, we'll get the correct results, and we don't have a problem, right? But are all RAW type of hazards, can all of them be solved by forwarding? Okay, if you recall, there was one case where we cannot solve. No matter what we do, we still have to provide a stall, and that was the case when memory gets involved. Okay, so there's a data dependency due to memory, then even RAW type of hazard will require a stall. So let's take a look at that example. Okay, so suppose you have load word R5, R3 of 20, followed by add R6, R7, R5. Okay, so here's the R5 is, we read the data from the data memory, put it in R5, and here R5 is being read. So we write to R5 in the load, but we are reading from R5. So again, this is an RAW type of hazard, right? If we examine it, this will be IF, ID, EX, MEM, and write back. If we examine this, IF, ID, EX, MEM, and write back. So first of all, do we have a problem? Normally we write the data to R5 when? End of the write back, correct? So this is where R5 is updated. And when are we trying to read it? We read R5 over here. So in clock cycle 3 we are trying to read R5, but it's being updated in R5, in the fifth clock cycle. So obviously we have a problem. If we try to read this, this will be the incorrect R5, not the updated R5, right? Can we do forwarding over here? When we do forwarding, we always look for when is the earliest the result that's needed is available. is the result that will go into R5 available over here? Yes and no. Okay, and the answer is no, because remember we have to read it from this memory. So if this is our data memory, okay, if this is the address R3 plus 20, suppose it contains, let's say, 7 in it. So this is 7 is what we need to go and put it over here. So have we read it from the memory at this point? No. All we have done is we have computed R3 plus 20, the address. When will we read the result from the memory? In the mem phase. That's when the data memory gets involved, right? So the answer is it's not available over here. Is it available over here? Is our data that will go into R5 available at the end of the memory phase? Yes, right? But when do we need it? In the add instruction, we need it in the ALU. So R5 is needed here. But it's available at the end of fourth. We need it in the beginning of fourth. Okay, so obviously, see, we cannot forward from here to here. Like this is future event. So there's nothing we can do. We have to wait one clock cycle. Okay, we have to put a stall in our pipeline. So the only way we can solve this problem is put a stall, which we indicate by a bubble. Then we repeat EX, mem, and write back. Even after we put a stall, we still have to forward the result from here to here. Otherwise, it will still produce the wrong answer. Okay? In terms of our hardware, what does that mean? See, if you take a look, here's our ALU. Here's our ALU out. Okay, in the next clock cycle, this will go to ALU out prime. Right? And here's the mux. Here's the mux. And before this, we have A and B and so on. Okay, so if you take a look, when the load word goes over here, so if the load word goes over here, this will produce R3 plus 20, right? And then this will go into the data memory and produce LMD. Okay, so let's pretend over here, so this is, if you recall over here, we had, let me add some more. Okay, here was our register array. So all the registers were over here. Here was our IR. Here was our instruction memory. And here was our program counter, right? So this is how we had created our pipeline. So let's take a look here. Load word has moved to this one. Okay, and let me put IR prime. And let me put over here IR double prime. And somewhere here, let me put IR triple prime. Okay, so this gets copied over here, this gets copied over here, and so on. Okay, so anyway, let's take the case load word is over here, and the add is over here. So add is over here, and load word is over here, right? So what will happen in the next clock cycle? Do we want the add to continue? If we let the add continue, right, what kind of result will it produce? Based on the old R5 or the R5 that the load is going to produce? See, this will be the old R5 if we let the add continue, right? So as you can see, add cannot move forward until we have read the data from the data memory. So let's pretend here is R3 plus 20. So, and we were going to read 7, and 7 was going to go into R5 as an example, right? So So load word will continue on and produce, for example, 7 over here, after reading the data from this in LMD, right? But add will stall, meaning it will basically circulate the data on itself. This will not move forward, this will not move forward. All of these will be stuck, and that's the meaning of this bubble. That anything before the EX, see this is our EX stage, anything before gets stalled, it stays in its place, stays in its place, right? Okay, so in the next clock cycle, now remember the load has already moved over here. And the result for whatever needs to go into R5 is here, right? So now can we let the add continue? Right? So we said yes, now it can continue. But as add continues, which R5 it should pick from? Should it pick it from the B register, or should it pick it from the LMD? LMD, because that's where the result was produced, right? So as you can see, this forwarding over here is actually a feedback from here to here. Okay, so this is our forwarding. Okay, so if the load word is followed by an instruction that uses the result of the load, then we have to feed back the LMD to the input of the ALU. And also we have to wait one more clock cycle by putting a stall. Okay? So our controller will issue a stall, meaning this column will not move forward. Will stay here one clock cycle. This column will not move forward. This column will not move forward. Right? So in our current design, once again, for the RAW type of hazards, for most of them, forwarding can solve the problem, and we don't have to put a stall. Okay, so forwarding can solve for most cases. No stall needed. Okay, but if load word is followed by an instruction that uses destination of load, okay, then both a stall and forwarding is needed. So this is an important point to remember. Load word is our most problem case. So if load word is followed by an instruction that uses the destination of the load word, then we have to have a stall, just like we saw over here, as well as we have to forward the data from the memory to the EX. Okay, and then, so how much of a performance slowdown this might be? Just to give you an idea, let's pretend 20% of the instructions are load word, right? And out of those 20%, let's pretend 30% of the time this type of scenario occurs where the destination of load is needed in the very next instruction. Okay, so 30% of load word have destination data dependency. So what slowdown this will cause us to have in our pipeline? So our CPI will become, okay, 80% of the time we are executing in one clock cycle, right? For the remaining 20%, we further said 0.2 times 0.7 is still 1, plus 0.2 times 0.3 is 1 plus 1. Because we have one stall for 30% of the remaining 20% instructions, right? So whatever number that comes out to. So that will be our effective CPI. So anyway, so we can always make a quick estimate of should we provide more hardware and what performance effect will it have on our current architecture, right? Okay, in our design right now, WAW is not a problem. This is a write after write. So if we did add R5, R3, R7, subtract R6, sorry, let's go subtract R5, R6, R4. So you can see we are writing to R5 and we are writing to R5 again, okay? Will this cause a problem? You can very easily see if I wrote it IFID, should start with IFID, EX, mem, and write back. This will start one cycle later, IFID, EX, mem, and write back. When are we writing to R5? At the end of the 5th clock cycle, right? Now, if this instruction was after the, if sub was after the add, the final result will be because of the sub, right? And you can see once we do the write back for the sub, it's one cycle later, so whatever the sub produces will be in R5. So that's why it's not a problem, right? But let me show you a case where this could be a problem, okay? At least not in our current architecture, but let me show you a case.
Professor, in the exams, are you going to provide us with these percentages, or are we going to make them up?
I will give you percentages, yes. Okay, so suppose, let's say we have our ALU. Okay, and let me assume add and subtract take one cycle, the equivalent of one cycle delay to produce the correct result, right? Let me pretend multiply takes 3 cycles to finish. The equivalent of 3 cycles, right? So now let's take a look over here. Suppose we have a add instruction, or suppose we have a multiply instruction. Followed by an add instruction. Both of them are trying to write to R7. So first we have a multiply instruction. Okay, let's pretend I'll pick some simple numbers. R3 has 5 in it, R5 has 10 in it. So what will it try to write to R7 then? 50, right? Suppose this has 7 in it, this has 5 in it, okay? Let me pick some other number, 9 in it, right? So what will it try to write to R7 then? 16, correct? Okay, so the question is, will it cause a WAW type of hazard? Okay, so let's take a look. This will be IFID, EX, mem, and write back, right? But we are assuming multiply takes 3 cycles. So instead of EX, how will we write it? EX1, EX2, EX3, mem, and write back. Right? 1, 2, 3, 4, 5, 6, 7 cycles. Okay, if we are doing the pipelining, this will start 1 cycle later. So this will be IF, ID. And how many cycles does add need? Just 1. So let's just say EX1 or EX, doesn't matter. Mem and write back. So my question is there a problem, or is this okay to execute like I showed you? Okay, if you bought this CPU, right? And you wrote this assembly language program. and you examined R7 at the end, what's the expected result? Forget the pipeline, forget what we did. If you were just a programmer, you wrote this instruction, it had 5 in it, 10 in it, 7 in it, 9 in it before you started executing your program, right? What's the final result that you will expect? 16, because this instruction came later, and whatever it produced in R7 should be the final answer, right? But what's our hardware going to produce? Take a look over here. It will produce 16 over here, correct? Once we do the write back. At the end of clock cycle 6, it will produce 16. But then at the end of clock cycle 7, what will it change it to? Remember, the multiply is finishing, so on the 7th cycle, so we'll end up writing 50 to R7, which is, so if you examine after the clock cycle 7, you'll find it to be 50, which is totally wrong, right? So this is an example of what kind of hazard? Write after write. So whenever the ALU operations take different amount of time, WAW hazards will come into play, okay? How do we solve this WAW hazard? Again, through comparators, we can recognize, see, once we go to the ID phase, right? We will know this is a multiply instruction, okay? So we will know what the destination is, as an example, in this case, R7. Very similarly, once we go to the add instruction, once we decode it, we know it's an add. We can check, does the destination here matches the destination of the previous instruction, okay? Through the IR and IR prime, okay? So if we do that, then basically what we have to do is we have to slow it down. So by putting a stall over here, keep in mind, anytime we put a stall is always put after the ID. Because before ID, we have no idea what the instruction is. Once we bring it into the IR register, we can examine the opcode, and then we can know if there's a data dependency or not. So stalls always occur after the ID, okay? So anyway, so in this particular example, we also have to know how many cycles the multiply will take, and based on that, we have to make sure that the write back over here finishes after the write back over here. So in this example, this will be IFID, EX1, mem, and write back. And through the comparators in the IR prime, IR double prime, we'll be able to detect there's still a WAW dependency and put 2 stalls and then let it continue. So now if we put 2 stalls over here, this one will work properly, okay? So the question is it better to have different instructions take different amount of time in the ALU to execute, or is it better to design the hardware where every instruction in the ALU takes the same amount of time? And the answer is this can be done, but it becomes more complicated, more hardware is needed. It's easier if we made every instruction in the ALU same amount of time and provided multiple ALUs. So that's much easier approach to designing, right? Okay, very similarly, our last category over here was for the data hazards, WAR, right after read. So the example would be something like add R5, let's say R3, R7, let's say subtract, right, okay, let's say R3, R7. Let me pick some other register, R3, R9, R12. Okay, so if you take a look over here, we are writing to R3 after reading from R3. Does reading change the data in a register? No. So this will never be a problem, okay? So never a problem. So to summarize, what kind of data hazards are a problem in our current design? Of course, RAW. Okay. Most of the RAW can be solved by forwarding, correct? So most of them can be solved by forwarding. There was one category where even the forwarding will not help, and that was when load was followed by an instruction that uses the destination of the load, right? So then we needed a stall in case of the load word data dependency, okay? WAW in our current design is not a problem because we are assuming every instruction in the ALU takes the same amount of time. But if we relax that instruction, then, relax that assumption, then WAW can start to become a problem, okay? So very briefly now, let me introduce the last category of hazards, which are called control hazards, and give you an idea of those. Okay, so the third category over here, if you recall, was control hazards. Okay, control hazard occurs due to branches and jumps. So if we have a branch instruction followed by another instruction, then that's where we can run into a problem, and that problem is referred to as a control hazard, right? So let me pick an example to clarify this. So suppose you have branch equal to Z R5 and some offset over here. So if R5 is 0, so remember the meaning of this was if R5 is equal to 0, then PC will become PC plus offset. And this offset is basically a 16-bit offset. Okay. Otherwise, PC will become PC plus 4, meaning we'll just continue normally, right? Okay, suppose after this one we have an add instruction. Add R7, R3, R5, subtract R6, R4, R8, multiply R12, R14, R16, and so on. Okay. And let's pretend the offset, if we add PC plus 4, takes us to a divide instruction. Divide R13, R17, R21. Okay. So if R5 is not 0, we'll continue executing in the normal order. If R5 is 0, then where should we go to? We'll go to jump to this instruction, right? So again, we can pretend, suppose this is at address 2000 hex, maybe this is at 3000 hex, okay? So just to make an easy example to understand, right? Okay, so let's see how this one will work, okay? So if we go to IF, ID, EX, mem, and write back. Okay. Okay, so if you recall in our data path, how do we take care of the branch instructions? Let me draw a quick picture over here. So we had PC going to instruction memory, going to IR. From here, we were picking A, picking B, IMM, IMM2, right? Then we had a MUX, ALU, out, and then here was our data memory and LMD, right? Okay, so for the branch instructions, if you recall, what we had was we had an adder over here for mux. Okay, so this is PC plus 4, if you recall. This is PC plus 4, right? And then basically this was, for a branch instruction, this was going over here, right? And then in this example, branch equal to Z R5 offset. So this will be our R5 in our current example. And then we had basically a 0 detector over here. And then this was basically a 1-bit flip-flop, which we called it a flag. Okay. So basically our hardware was going to check this. If this is 1, we have to take the branch. If this is 0, we just continue normally and we'll update the PC with PC plus 4, right? And this 16-bit offset over here will come into this. So from here, the 16-bit offset will come over here, and this one will go over here. So in this example, this one will produce PC plus 4 plus 16-bit offset. If the branch is going to be taken, then this path over here will go back and update the PC. So that was the idea, right? Okay, so so now let's take a look over here. If this is our branch instruction, right? If we were executing normally, what will happen? This will go IF, ID, EX, mem, and write back. This will go normally IF, ID, EX, mem, and write back. Okay, so here's where the problem is. Okay, for a branch, in which clock cycle do we know that the branch is successful or not? Meaning, we have to update the PC to the target PC plus 4 plus 16-bit or PC plus 4. When do we make that decision? Okay, let's take a look. We know it's a branch instruction, right? In the EX phase, what will the ALU produce? PC plus 4 plus 16-bit offset, correct? Okay, also the flag will be 1 or 0, right? So you can see in the 4th cycle, 1, 2, 3, 4, we will update the PC. Okay, to whatever the correct value is. If the flag is 0, we will update it to PC plus 4. If the flag is 1, we will update the PC to PC plus 4 plus the target address. So at the end of the 4th cycle is when we update the PC. However, the problem is, so at the end of the 4th, right? At the end of 4th cycle. But the problem is, if you take a look at the add instruction in the 4th cycle already has gone through the EX phase. Any instruction that goes through the EX phase basically ends up modifying the ALU out, right? So if we let the add continue, you will see we'll end up replacing R7. Okay, but if the so what I'm trying to say is like this. Let's assume R5 is 0. Right? So what will happen after the 4th cycle? After the 4th cycle, PC will change to what? In this example, 3000, right? But by the time we reach the 4th cycle, we've already updated this to R3 plus R5, okay? Now if we try to fetch this instruction, so basically this will now go into the next phase. By the time we decode this instruction, we'll end up updating R7, which is totally wrong, okay? So the problem is the next instruction gets executed because We don't know what should be the target PC or what should be updated in the PC. We need 4 cycles to make a decision. So one solution is to solve this problem is, as soon as we decode and we find out it's a branch instruction, okay, don't do anything, because we don't want the answer to be wrong. So what we'll do is, at the end of ID, we know it's a branch instruction. So we will start to basically put bubbles over here. After this, we will now fetch again. And the reason is because if R5 was 0, remember we are going to update the PC at the end of 4. So it will become 3000. So we have to fetch it again so that it can execute this instruction correctly. So IF, ID, EX, mem, and write back. Okay, that means once a bubble occurs, the next instruction has to start again over here. So this will basically be bubble, 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 1 cycle later, right? So effectively, as you can see, how many cycles did we end up wasting? Because we refetched it, right, over here. So think of it as if the first 3 cycles were wasted. So for example, let's say 20% of the instructions are branches. Okay? Or let me make it 30% to emphasize my point. Then what will it affect the CPI? 70% of the time it's 1 cycle. 30% of the time it's 1 plus 3, because we wasted 3 cycles because we have to refetch it, because we don't know whether it will be executing the add or whether it will be executing the divide. We have to wait until the PC gets updated, right? So what does that CPI come out to? 1.9. So 90% reduction in our performance just because of the branch instructions, right? So 1 more minute, then I'll stop and continue on this one. So now let me give you the solution. So obviously this is a poor solution to basically don't do anything after the branch for 2 cycles, then fetch it again. That's equivalently wasting 3 clock cycles. Okay. So what we can do is we can do a few interesting things. Okay. One possibility is to make the decision whether we should take the branch or not. Rather than doing it at the end of the EX phase, let's do it early. Meaning directly go to a register. So see, I forgot there's a register array over here. So rather than copying the register into A, then applying a 0 detector, let's apply a 0 detector right over here. And put the flag right over here. So move the flag 1 cycle earlier. Okay. Also, the target address, let's provide another adder. Let's not use this ALU. Provide another IMM. So if we provided another adder over here, so this will do IMM 2 plus PC plus 4. So in other words, rather than doing it in the EX phase, we're moving it to the ID phase. So this will save 1 clock cycle. But still we will need 1 stall instead of 2 stalls. So this will become 2. So still it will not be as good, right? Okay. The other option is let's continue executing normally. So we always execute it normally. So regardless we were supposed to go over here or not. Okay, what happens if we find out as we are executing is that no, we were not supposed to execute it, we were supposed to execute this instruction, right? What we'll do is, some of you who have done assembly language programming before would remember in most of the microprocessors there's an instruction called no-op. Okay, it doesn't do anything. Okay, usually has an opcode of all zeros. So remember we have a 6-bit opcode over here. So here the basic idea is like this. And this is called branch prediction. And I'll go over it again, but let me just at least give you an initial idea of it. So in branch prediction, we are basically gambling. We are saying branch will not be taken, okay? Meaning R5 will not be 0. So we'll just continue to execute the normal pipeline, okay? As we go through the third cycle and we find out, oh no, R5 is in fact 0, right? Because remember we have provided extra hardware here so that earlier we can detect if it's 0 or not. So as soon as we find out we made the wrong decision, what we'll do is we'll change the opcode for this. Change the opcode to 000. So we'll still let it continue, but it will not do anything, it will not modify any register, right? And now the next instruction automatically, because by that time we have updated the target address, it automatically will become this instruction. So as I will show it to you next time. So this way we can avoid any delay in our pipeline. Okay? All right, so we'll continue from this point.